autumn of 1940, Britain stood alone. Across the Channel, the Luftwaffe had already lost the Battle of Britain, but no one in Whitehall was celebrating. The reason was sitting on Ernest Hives's desk at Derby. Rolls-Royce could not build Merlin engines fast enough. Not because the design was flawed, not because the factories had been bombed, but because the most powerful industrial nation in the world, the United Kingdom of Great Britain, did not possess the machine tools, the precision gauges, or the production capacity to manufacture its own war-winning engine at the rate the war demanded. By the summer of 1941, Fighter Command needed 500 Merlin engines per month to sustain operational strength. Rolls-Royce, working 3 shifts a day across Derby, Glasgow, and Crewe, could deliver 340. The gap was 160 engines. 160 Spitfires and Hurricanes that would never fly. 160 gaps in the line. Hives did not go to the Treasury. He did not go to the Air Ministry. He crossed the Atlantic, and he went to a motorcar manufacturer in Michigan that had never built a single aero engine in its history. The company was Packard. The agreement they signed in September 1940 would reshape the air war over Europe, rearm the United States Army Air Forces, and transform a mediocre American fighter into the finest long-range escort aircraft of the Second World War. But the real story of the Packard Merlin is not the engine itself. It is the story of what happens when the genius of British engineering meets the sheer unrelenting scale of American industry, and what Britain was quietly forced to admit about itself in the process. In the spring of 1940, the Royal Air Force faced a problem that had nothing to do with courage tactics or the quality of its aircraft. It had everything to do with machine tools. The Merlin engine, the 12-cylinder supercharged, liquid-cooled power plant that drove the Spitfire, the Hurricane, and the Lancaster, was arguably the finest aero engine in the world. Rolls-Royce had spent the better part of a decade refining it from the earliest Merlin one of 1936 through successive marks that wrung ever greater power from the same fundamental architecture. By 1940, the Merlin III was producing 1,030 horsepower. By 1942, later marks would exceed 1,600. The trajectory was extraordinary. But trajectory meant nothing if the engines could not be built in sufficient numbers. Rolls-Royce had been founded in 1906, the product of a partnership between Charles Rolls, the aristocratic motoring enthusiast, and Frederick Henry Royce, the self-taught engineer from Lincolnshire, who could not abide imprecision. Their Derby factory, established on Nightingale Road, had grown from a small precision engineering works into one of Britain's most important defence manufacturers. By 1939, a second Merlin facility had been established at Crewe and a third at Glasgow, the latter operated under an arrangement with the Hillington Industrial Estate built specifically to expand wartime aero engine output. 3 factories, tens of thousands of workers, and still not enough. The fundamental constraint was not workforce. It was tooling. The Merlin demanded tolerances measured in thousandths of an inch. Its cylinder blocks its crankshaft, its supercharger impeller. Each component required specialized machine tools of a precision that British industry, stretched across a dozen competing wartime programs, could not supply fast enough. Lord Beaverbrook, appointed Minister of Aircraft Production by Churchill in May 1940, understood the numbers immediately. He drove Rolls-Royce and its subcontractors relentlessly and concluded within weeks of taking office that British industrial capacity alone could not close the gap. The air staff requirement was unambiguous. Fighter Command needed a sustained delivery rate of 500 Merlin engines per month to maintain operational readiness. Bomber Command's expanding Lancaster program added further pressure. The figure Rolls-Royce could achieve by mid-1941 across all 3 factories operating continuous shifts was approximately 340 engines per month. The arithmetic was brutal and did not improve with optimism. It was Beaverbrook who first raised the possibility of American production. Ernest Hives, chairman of Rolls-Royce, a blunt Yorkshireman who had driven test cars at Brooklands before the First World War, and who trusted engineering data above all other forms of argument, was not instinctively enthusiastic. Rolls-Royce had built its reputation on the proposition that precision engineering was a British virtue practiced at Derby and nowhere else. The idea of handing the Merlin's blueprints to a foreign manufacturer carried implications that were commercial, institutional, and, for a company of Rolls-Royce's particular pride, almost psychological. But Hives read the same production figures Beaverbrook read, and he made the decision that only a man entirely free of sentiment could make. In the summer of 1940, Rolls-Royce approached the Packard Motor Car Company of Detroit, Michigan. Packard had no history of aero-engine manufacture. It built luxury automobiles, the Packard 12, favored by American presidents and Soviet marshals alike. What it possessed in abundance was precisely what Rolls-Royce lacked: vast precision machine shops, a workforce trained to automotive tolerances that approach, though did not yet meet aero-engine standards, and the production management infrastructure to scale rapidly. 3 American manufacturers were assessed. Ford was approached and declined, reportedly unwilling to accept the production specifications without substantial redesign. Studebaker was considered and set aside. Packard was selected in part because its engineering director, Jesse Vincent, grasped the Merlin's architecture immediately and did not ask for simplification. The contract was negotiated through the British Purchasing Commission in Washington, with the Air Ministry providing technical support. Its value was established at approximately £6.5 million in 1940, the equivalent, by modern calculation, of roughly £320 million today. The agreement, signed in September 1940, gave Packard the right to manufacture the Merlin under license. Rolls-Royce would supply drawings, technical advisors, and critically sample engines to be stripped and measured at Detroit. Packard would convert its manufacturing lines, acquire the necessary tooling at American industrial scale, and deliver engines to a specification controlled line by line from Derby. What Packard received was not a simple blueprint. The Merlin drawings ran to tens of thousands of individual sheets. Many dimensions were specified in British imperial fractions that had no direct American equivalent. Packard's engineers spent the first months of the program converting the entire specification to American standard measurements, a task that, if done carelessly, would have introduced cumulative errors that destroyed the engine's performance. It was done with extraordinary care. The first Packard-built Merlin ran on a test stand in Detroit in August 1941. It produced full-rated power on its initial run. The program had its foundation. The production line was about to begin. To understand what Packard achieved, it is necessary to understand what the Merlin actually was, not as a symbol, but as a physical object that had to be manufactured to tolerances that in 1940 pushed the limits of what any precision engineering facility in the world could reliably achieve. The Rolls-Royce Merlin was a V12 liquid-cooled piston engine, 12 cylinders arranged in 2 banks of 6 set at a 60-degree angle with a total swept displacement of 27 liters. Displacement in this context is the total volume swept by all pistons through their full stroke, a measure of the engine's fundamental breathing capacity. At 27 liters, the Merlin was not the largest aero engine of the war. What distinguished it was the supercharger. A supercharger, in plain terms, is a mechanically driven air compressor mounted to the engine's intake. At altitude, air becomes thin. Thin air means less oxygen. Less oxygen means less combustion and therefore less power. A supercharger compresses the incoming air before it enters the cylinders, restoring and ultimately exceeding sea-level combustion density at heights where unsupercharged engines become sluggish and ineffective. The Merlin supercharger was a centrifugal design driven off the crankshaft with an impeller, a rotating disc with precisely curved vanes, spinning at speeds that in later 2-stage versions exceeded 30,000 revolutions per minute. The 2-stage 2-speed supercharger, introduced in the Merlin 60 series from 1941 onwards, was the single most important development in the engine's history. It was designed by a Rolls-Royce team led by Cyril Lovesey, who had joined the company in 1932 and who was responsible for much of the Merlin's wartime development. The two-stage system used two supercharger impellers in sequence, the first compressing the air, the second compressing it again with an intercooler between them to reduce the temperature that compression inevitably generated. The result was an engine that produced more power at 30,000 feet than the Merlin III had produced at sea level. The operational significance of this was immediate and decisive. The Spitfire Mark V, powered by the single-stage Merlin 45, had been outclassed at high altitude by the Focke-Wulf FW190 from the autumn of 1941. The Spitfire Mark IX, powered by the two-stage Merlin 61, restored British air superiority. The margin at 30,000 feet was not marginal. It was by the test figures compiled at Boscombe Down in the spring of 1942, approximately 30 miles per hour in level flight and a markedly superior rate of climb. It was this engine, the two-stage Merlin in its 60 series configuration, that Packard was eventually tasked to manufacture as the V165, or the American military designation for the Packard-built Merlin. The conversion of the Merlin from British to American production standard required Packard to solve three categories of problems simultaneously. The first was dimensional. British engineering drawings of the period used fractional imperial measurements, 16ths, 32nds, 64ths of an inch, that did not map directly onto American decimal equivalents. Packard's engineering team under Vincent's direction converted approximately 31,000 individual dimensions to American decimal standard. Each conversion was checked independently. The tolerance stack, the cumulative effect of small measurement differences across hundreds of components, was calculated and controlled. The work took 6 months. The second problem was metallurgical. Several Merlin components used British alloy specifications that had no direct American equivalent. The cylinder block cast in a high-silicon aluminium alloy, and the crankshaft forged in a specific chromium molybdenum steel required Packard to work with American suppliers to produce materials that met British mechanical properties without replicating British compositions. The solutions were in several cases technically superior to the originals, a point that Rolls-Royce engineers visiting Detroit in 1942 noted with a combination of admiration and competitive unease. The third problem was scale. Rolls-Royce's Derby factory at peak wartime production employed approximately 14,000 workers and produced roughly 500 engines per month across all marques. Packard's Detroit facility, once fully converted, employed 9,000 workers on the Merlin program, alone a smaller workforce producing a comparable output because American mass production methods applied to aero engine manufacture achieved cycle times that British craft production practices, for all their precision, could not match. The first production, Packard Merlin, designated the V16501, was delivered to the British Purchasing Commission in August 1941. It was installed in the Avro Lancaster Mark III, replacing the Rolls-Royce Merlin 20. The two engines were to within the measurement capability of the period identical in performance. The Lancaster Mark III equipped No. 44 Squadron at RAF Waddington, No. 97 Squadron at RAF Woodhall Spa, and No. 207 Squadron at RAF Spilsby III of Bomber Command's frontline units through 1942 and into 1943. But the engine that would define the Packard Merlin's legacy was not the V16501. It was the V16507. The American-built version of the two-stage Merlin 66 and the airframe it was about to transform was not British at all. The decision was made. The production line had its engine. And in a North American aviation facility in Inglewood, California, the airframe that would carry it was waiting. By the end of 1942, Packard had delivered 5,400 armored 21 Merlin engines to British and American operators. By the end of 1943, the cumulative total exceeded 25,000. By VJ Day in August 1945, Packard had manufactured 55,523 Merlin engines, roughly 1 in every 4 Merlins built during the entire war. The numbers require context to be understood. Rolls-Royce, across its Derby, Crewe, and Glasgow factories, produced approximately 113,000 Merlins during the same period. Ford's shadow factory at Trafford Park, Manchester, established under a separate arrangement in 1940, added a further 30,000. Total British Merlin production reached approximately 143,000 engines. Packard's 55,523 represented an additional 39% of that figure. Without Packard, RAF Bomber Command's expansion program of 1942 to 43, the period when Harris's crews were sustaining losses that consumed aircraft and engines faster than any pre-war planner had modeled, would have been unsustainable. The Lancaster alone required 4 Merlins per airframe. At peak production in 1943, Avro was delivering approximately 150 Lancasters per month. That figure demanded 600 Merlin engines per month for Lancaster production alone before a single engine was allocated to Spitfires, Mosquitoes, Hurricanes, or Halifaxes. The arithmetic of strategic bombing was at its foundation the arithmetic of engine supply. Packard engines powered Lancaster Mark IIIs and Mark Xs throughout Bomber Command's main offensive. Number 617 Squadron, the Dam. Busters flew Lancasters, powered by a mix of Rolls-Royce and Packard Merlins, on the night of 16th to 17th May 1943. The distinction was operationally invisible. The engines were to all measurable purpose the same. The Mosquito de Havilland's extraordinary twin-engine light bomber and long-range fighter was similarly equipped. Packard Merlins powered the Mosquito Mark IX and Mark XVI variants, used by No. 105 Squadron and No. 109 Squadron in the Pathfinder Force units, whose precision marking of targets preceded the main Lancaster and Halifax stream on most major Bomber Command raids from mid-1943 onwards. In fighter command, the supply chain was equally critical. The Spitfire Mark IX, powered by the Merlin 61 or 63, both manufactured at Derby and Packard, became the standard RAF day fighter from the summer of 1942. By early 1943, Spitfire Mark IXs equipped No. 64 Squadron at RAF, Fairlope No. 122 Squadron at RAF, Hornchurch No. 331 Squadron, the Norwegian manned unit at RAF North Weald, and No. 611 Squadron at RAF Digby, among dozens of others. The Packard-sourced engines within this fleet were indistinguishable in service from their Derby equivalents. Maintenance schedules, overhaul intervals, and performance data were common across both origins of manufacture. But the transformation that most altered the course of the air war did not occur over Britain or over Germany or over the North Sea. It occurred in Inglewood, California, in the late autumn of 1942. The North American P-51 Mustang had entered service with the RAF in 1942 as a tactical reconnaissance and ground attack aircraft. It was fast at low altitude maneuverable and possessed an exceptional fuel capacity for an aircraft of its size. It had one fundamental flaw. Its Allison Fire 1710 engine, a capable American power plant, lost performance dramatically above 15,000 feet. The Allison was a single-stage, single-speed supercharged engine. At the altitudes required for escort operations over defended German territory, 25,000 to 30,000 feet, the P-51A was operationally marginal. 2 RAF officers, Ronald Harker of Rolls-Royce and Ian Campbell Ord of the Air Fighting Development Unit, flew the Mustang in April 1942 and reached the same conclusion independently. The airframe was exceptional and the engine was wrong. Harker wrote a memorandum circulated within Rolls-Royce and to the Air Ministry in May 1942, calculating that a Merlin-engined Mustang would achieve approximately 400 miles per hour at 25,000 feet with a combat radius carrying external tanks of approximately 850 miles. 850 miles from British bases reached Berlin and returned. The conversion program proceeded with a speed that Whitehall procurement rarely matched. 5 Mustang Mark I airframes were modified to accept the Merlin 65 at the Rolls-Royce facility in Hucknall, Nottinghamshire, in the autumn of 1942. The first flight of the Merlin Mustang occurred on the 13th of October 1942. The performance figures confirmed Harker's calculations precisely. North American Aviation adopted the installation for production fitting the V165-0-3, the Packard-built equivalent of the Merlin 68 to the P-51B and P-51C. The V165-0-7 equivalent to the Merlin 66 powered the definitive P-51D from 1944. At 30,000 feet, the P-51D achieved 437 miles per hour in level flight. Its combat radius with drop tanks exceeded 950 miles. It could escort Boeing B-17 Flying Fortresses and consolidated B-24 Liberators from English bases to any target in Germany and return. The operational consequence was decisive. 8th Air Force bombing campaigns of 1943, conducted without adequate fighter escort above 400 miles from base, had sustained losses of between 6 and 9% per mission. At that attrition rate, crews were statistically unlikely to complete their required 25 mission tours. The campaigns against Schweinfurt in August and October 1943 had cost 120 heavy bombers in 2 raids losses that the American strategic bombing program could not sustain indefinitely. P-51 D operations beginning in December 1943 transformed those figures. By February 1944, 8th Air Force could provide continuous escort to Berlin. Luftwaffe day fighter losses, forced to engage the Mustangs rather than the bombers, reached unsustainable levels through the spring of 1944. The air superiority established over the Reich by June 1944 was in no small measure the product of a Packard-built engine installed in an American airframe conceived by a British engineering insight. The contractor at peak production employed 40,000 workers across its Detroit and Utica facilities, of whom approximately 9,000 were dedicated to the Merlin program. Packard delivered engines at a rate that by 1944 reached 1,400 per month, more than Derby, Crewe, and Glasgow combined had achieved at any single point in 1941. The subcontractor network supplying components to Packard's Merlin line extended across 7 American states, supporting an industrial web that had no British equivalent in scale. At peak, the Packard Merlin powered aircraft in 4 distinct Allied air forces simultaneously: the RAF, the Royal Canadian Air Force, the Royal Australian Air Force, and the United States Army Air Forces. It flew combat operations over Western Europe, the Mediterranean, North Africa, the Eastern Front, where Merlin-powered aircraft were supplied to the Soviet Union under Lend-Lease and the Pacific. No single aero engine of the Second World War was more widely distributed across Allied operations. Rolls-Royce watched the scale of American production with an emotion that combined gratitude and institutional discomfort in roughly equal measure. The first signs of a different kind of problem were already visible in the production figures of 1943. The Merlin's design was advancing rapidly. New marks were emerging from Derby every few months, each incorporating hard-won development from operational experience. The task of communicating those changes to Packard, converting them to American standard, and incorporating them into a production line operating at maximum rate created a coordination burden that neither company had fully anticipated when the agreement was signed in 1940. It was a problem of success, and it was about to become considerably more complex. The Packard Merlin program did not end in a Whitehall cancellation or a parliamentary statement. It ended as all wartime industrial arrangements must end when the war itself concluded. But the path to that conclusion was neither straightforward nor free of conflict, and what happened in the final years of the program revealed tensions that the urgency of 1940 had temporarily suppressed. The fundamental difficulty was one that Ernest Hives had understood from the beginning and had chosen to accept because the alternative insufficient engine supply was worse. Rolls-Royce had licensed its most valuable and strategically critical design to an American manufacturer. That manufacturer had over 4 years of production accumulated an engineering knowledge of the Merlin that rivaled Derby's own. Packard's engineers had solved problems with the engine's manufacture that Rolls-Royce had lived with for years. Several of Packard's production solutions in alloy formulation, in machining sequence, and quality control methodology were adopted back into British production practice. That transfer of knowledge was commercially inconvenient. It was strategically significant, and it was irreversible. By 1944, Packard was in quiet discussions with the United States Army Air Forces about the possibility of post-war production. The Merlin's performance envelope was not yet exhausted. The two-stage, two-speed variants had demonstrated that further development was possible, and American operators, having flown the engine in the P-51 through 2 years of combat, had developed an institutional familiarity with it that created natural post-war demand. Rolls-Royce's position under the terms of the original license was defensible but uncomfortable. The coordination problem worsened as the pace of Merlin development accelerated through 1943 and 1944. Derby was producing a new major mark every 3 to 4 months. The Merlin, 61, 63, 66, 70, 76, and 85. Each represented significant engineering changes. Alterations to the supercharger gear ratios, modifications to the intercooler layout, revised ignition timing changes to the reduction gear ratio at the propeller shaft. Each change required a full drawing revision package to be transmitted to Detroit, converted to American standard, reviewed by Packard's engineering team, approved by USAAF Inspection Authority, and incorporated into the production line without disrupting output. The system worked, but it worked at a cost in engineering hours, transatlantic communication, and institutional trust that neither party had budgeted for in 1940. There were disagreements about performance ratings. The USAAF permitted higher emergency boost pressures in the V1 650-7 than Rolls-Royce had authorized for the equivalent Merlin 66 in RAF service, a decision driven by operational requirement that Rolls-Royce regarded as a threat to engine reliability and therefore implicitly to the Merlin's reputation. The argument was conducted through official channels. It was never publicly acknowledged by either party. There were disagreements about overhaul intervals. Packard's production line approach to quality control statistical sampling rather than individual inspection of every component had been validated by operational experience. Rolls-Royce's culture of individual component certification resisted the implication that American methodology was adequate. The argument was at its foundation not about engineering, but about identity. The end came quickly when it came. The Japanese surrender in August 1945 rendered the question of post-war American Merlin production academic almost overnight. USAAF contracts for the V1 650 were cancelled within weeks. Packard's Merlin production lines, which had been operating at full capacity as recently as June 1945, building engines for aircraft that would not now be needed, were shut down in an orderly sequence through the autumn of 1945. The final Packard-built Merlin was completed in October 1945. The total production figure was 55,523 engines. The production lines were dismantled. The tooling was scrapped or sold. The drawings were returned to Rolls-Royce. The American engineers who had spent 4 years mastering the Merlin's manufacture were reassigned. Packard returned to building luxury automobiles. The license agreement lapsed without renewal. The factories fell silent. The war was over. The Packard Merlin program left 4 legacies, none of them fully visible to the people who created them. The first was operational. 55,000 engines delivered over 4 years sustained Allied air campaigns at a tempo that British production alone could not have supported. The Lancaster offensive, the Spitfire's air superiority campaign over occupied Europe, and most consequentially, the P-51 escort missions that broke the Luftwaffe's day fighter force in the spring of 1944, were all in varying degrees products of Packard's Detroit production lines. The argument that the air war in Europe was won in part at a motorcar factory in Michigan is not rhetorical. It is industrial history. The second legacy was technological. The process of converting the Merlin to American manufacture, the dimensional standardization, the metallurgical adaptation, the statistical quality control methodology advanced American precision engineering practice in ways that outlasted the program itself. Packard's engineers returned to automotive production, carrying knowledge of manufacturing tolerances and quality systems that had been forged in the most demanding production program of the war. American manufacturing's post-war reputation for scale and precision owed something, not everything, but something to what was learned on the Merlin line. The third legacy was the P-51 Mustang. It is worth stating plainly, without the Packard-built Merlin, the P-51 would have remained a capable but altitude-limited tactical aircraft. The V-165-0-7 transformed it into the instrument that made deep strategic bombing survivable. The P-51D's combat record and the Strategic Air Campaign's ultimate contribution to German industrial collapse cannot be separated from the engine that powered it. The Merlin's greatest operational achievement may not have been the Battle of Britain. It may have been Berlin. The fourth legacy was one that Rolls-Royce preferred not to examine too directly. The Packard program had demonstrated irrefutably that the Merlin could be manufactured to full specification by a company that had never built an aero engine before 1941. The mystique of British precision engineering, the proposition that what was made at Derby could only be made at Derby, had not survived contact with Detroit. Rolls-Royce remained a great company. The Merlin remained a great engine. But the idea that greatness in design automatically conferred exclusivity in manufacture had been tested and found wanting. Ernest Hives understood this. He had made the decision knowing what it meant. His post-war correspondence held in the Rolls-Royce Heritage Trust Archive at Derby reflects a chairman who took satisfaction in what the program had achieved and a degree of equanimity about what it had revealed. Hives retired from Rolls-Royce in 1957, elevated to the peerage as Baron Hives of Duffield. He had, in the judgment of every procurement historian who has examined the period, made the correct decision in 1940 and made it with a clarity that the institutional culture around him would not have permitted had he consulted it too widely. The human footnote belongs not to Hives, however, but to Ronald Harker, the Rolls-Royce test pilot and liaison officer, whose April 1942 memorandum first proposed the Merlin Mustang conversion. Harker spent the remainder of the war arguing in successive internal documents for the strategic potential of the Merlin-engined P-51. He received no official recognition for the insight that arguably shortened the European Air War. His memorandum was declassified, and his contribution formally acknowledged only in the 1970s when he was in his 60s. He died in 1995, having spent his retirement writing a book, Rolls-Royce from the Wings, that documented with characteristic understatement the episode for which he deserved rather more credit than he received. The honest verdict on the Packard Merlin program by the standard of the procurement historians who have examined it most carefully is straightforward. It was necessary, it was well executed, and it was, from the perspective of both nations, a success without precedent in the history of licensed aero-engine manufacture. The Merlin's design was British. Its production at the scale the war required was not. Both facts matter equally. Neither diminishes the other. What the program proved, and what Whitehall has periodically preferred to forget in the decades since, is that industrial capacity and engineering excellence are different things. Britain has, in the post-war period, continued to produce engineering excellence of the highest order. The capacity to manufacture that excellence at scale in sufficient numbers on the timelines that conflict demands is a different question, and one that defense procurement ministers have answered with varying degrees of conviction ever since the autumn of 1945, when Packard's Merlin line went dark and the drawings came home to Derby. If you found this history valuable, give the video a like. It is the single best signal you can send this channel. And if you want more stories about the aircraft, the engines, and the decisions that shaped British military power, subscribe to UK Defence Archive. We will see you in the next one. Somewhere over the North Sea in the winter of 1944, a P-51D Mustang climbed through broken cloud at 28,000 feet. Its Packard-built Merlin turning at 3,000 revolutions per minute. Its pilot scanning the bomber stream below for the first sign of German fighters, listening as every Merlin pilot listened to the engine note that told him with absolute authority whether the machine beneath him intended to bring him home.